Hello, everybody. My name is Gong Yishen, and we are representing Group Monash. And then today I'll be talking about green steam cracking furnaces, and then we'll be introducing two new technologies to it, which is hydrogen and electrical cracking. Now, as an introduction, my name is Gong Yishen. I am the team leader, and then we have five people in our team, which is Yonglin, Elaine, Tan Kai En, and Ru Wei. Now, today we'll be talking about naphtha steam cracking. We will be comparing four different methods, base case, and two different hydrogen methods, and an electrical method cracking.
My name is Tan Kai En, and I'll be talking about conventional naphtha cracking, which is the base case used in our simulation. All the processes in our team's simulation were conducted in Aspen Plus, and the main property method used for all the simulations is Pang-Robinson equation of state. The following is a list of the general assumptions used in the simulations, and for the base case, conventional naphtha steam cracking was simulated with a steam cracking furnace as the main simulation aspect. Steam cracking is typically conducted in a cracker furnace using fire heat from the combustion of fuel such as natural gas or coal. Thermal cracking reaction in the presence of steam occurs without catalyst in the radiant section of the furnace, which results in the production of ethylene and other byproducts, with the major components shown in the table below. The main compartments of the cracking furnace are the convection section and the radiant section. The combustion fuel used in the simulation is natural gas, and as seen in the process flow diagram here, the naphtha stream and the process water used to dilute the naphtha stream are boiled and preheated in the convection section of the furnace, which is then mixed together before it is preheated again and transported into the radiant section of the furnace, where the main reaction would occur. The products are then rapidly cooled in the transfer line exchanger to stop the reaction, and the products are sent for further refining and separation. Some other assumptions used can be seen here, and for the naphtha feedstock, it only consists of hydrocarbon components, mainly of C3 and above. The components of C5 and above are simulated using pseudo components, and the steam to naphtha feed ratio is 0.5:1, and both the feed streams are pressurized to 5.8 bars before they are preheated and mixed. In this simulation, the preheating of the feed streams and further heating of the mixed streams in the furnace convection section is simulated using heat exchanger blocks with flue gas from the natural gas combustion as the heat stream. The steam addition into the naphtha feed is simulated using a mixer block, and the cracking reaction is simulated using an R-plug block with co-current thermofluid flow with flue gas as the thermofluid, where the configurations and parameters are shown here. The reaction kinetics uses a molecular reaction scheme developed by Kumar and Kunzru, and the pseudo components undergo a primary cracking reaction to form hydrogen and hydrocarbons of C4 or less. Secondary reaction converts primary cracking products into secondary products, and the details for both reactions can be found in Appendix B5. Rapid cooling of the cracked products in the TLE is simulated with a heat exchanger block, and the cracked gas is cooled to 380 degrees Celsius using high pressure water as the cooling stream to produce high pressure steam for an adjacent process.
Hi, I'm Elaine, and I will be presenting the first proposed hydrogen generation method, which is the steam methane reforming. Natural gas is used as the feedstock because it has the higher hydrogen to carbon ratio and fewer carbon deposition problems than other feedstocks such as naphtha. Firstly, sulfur compound in natural gas need to be removed as it is corrosive and will deactivate the catalyst. The hydrogen sulfide will react with the zinc oxide to form solid zinc sulfide, which can be easily removed by the cyclone. The following reaction is steam methane reforming. Heavier hydrogen carbons such as ethane, propane, butane, and so on will be fully converted into methane. The methane will react with the steam to form carbon monoxide and hydrogen with an efficiency of 95% using rhodium under the following condition. The remaining gas is being sent to the water gas shift reactor. The catalyst used in this reaction is copper manganese cerium oxide mesoporous catalyst, as it has 100% of CO conversion and without any methane production. Since the steam methane reforming releases large amount of CO2, so it has to be removed. The CO2 is captured by reacting with the calcium oxide to form solid calcium carbonate, which can be separated from the gas stream in a cyclone. The calcium oxide is then regenerated by calcinating calcium carbonate. The calcium oxide is selected as it has high CO2 capacity and fast kinetic of CO2 absorption. The gas stream from the cyclone is then being sent to a flash tank for water removal. Hydrogen produced has purity of 46%. There are also some operational challenges. For example, steam methane reforming will produce a large amount of CO2. The removal of CO2 requires significant energy input, so increasing the operational cost. However, by applying the chemical looping combustion, the required calcination energy can be supplied by the CLC system, using nickel as oxide carrier between the fuel and air reactor.
My name is Yuruwei and I'll be presenting the next part, which is hydrogen generation via plastic gasification. The process flow diagram is shown with abbreviations used, process inlets and outlets. The key assumptions of this simulation include 100% efficiency of gas-solid separation and 100% water removal during drying. Plastic waste was selected as the feedstock as it is readily available at a low cost. As polyethylene is the most common plastic, feedstock composition is simulated using equal parts of HDPE and LDPE. This method aligns with the Malaysia Plastic Sustainability Roadmap to achieve plastic circularity by the year 2030. After drying, the feedstock undergoes thermal decomposition, where non-conventional plastic waste is degraded into carbon, hydrogen, nitrogen, oxygen, and sulfur. Steam gasification with a 4:1 steam to carbon molar ratio then takes place in a fluidized bed reactor. Due to the use of nickel catalyst, it is assumed that the gasification process does not produce tar or ammonia. Solvents are used to clean up hydrogen sulfide and carbon dioxide in the syngas. As solvents are not regenerated for the reasons mentioned, used solvents such as zinc sulfide and calcium carbonate are sold to generate side revenue. A steam methane reformer is employed to remove methane formed due to carbon monoxide methanation during desulfurization. Due to the use of a catalyst with low methane selectivity, it is assumed that methanation does not occur during water gas shift. After condensation at low temperatures to remove water, the product gas produced has around 34% hydrogen, 64% water, and 2% methane, which is sufficient purity for boiler combustion. In reality, molten plastic waste may create reactor feeding problems, and the gasification catalyst may suffer deactivation due to sulfur content in the feedstock. Appendix A2 shows the actual carbonation process will require 1.28 times the amount of calcium oxide in simulation, which increases the production cost. Potential improvements to the process include the use of plasma reactors and chlorine removal units, so that the process can accommodate real-life mixed plastic waste containing PVC plastic. Comparing both methods of hydrogen generation, other than having no direct emissions, plastic gasification is inferior to steam methane reforming in terms of hydrogen yield, indirect emissions, and energy requirements. Hence, steam methane reforming is the chosen method for hydrogen production.
Hi, my name is Yonglin and I'll be going through hydrogen-based cracking as well as electric-based cracking. Both of these cracking methods are similar to that of base case and only differs in method of heating. Due to high heating requirement of naphtha cracking process, conventional furnace that uses fire duty produces significant amount of flue gas which contributes to greenhouse effect. In hydrogen-based cracking, hydrogen gas from steam methane reforming or plastic gasification is used as fuel instead of natural gas as in base case. By doing so, the combustion product with air will mainly consist of steam and nitrogen gas. For the simulation, about 3.5 tons per hour of hydrogen gas from hydrogen production process undergoes combustion with 65 to 80 tons per hour of air, simulated with a R-Gibbs block. This combustion product of different composition will be used to heat up process streams. As the adiabatic flame temperature of hydrogen gas in air is higher than natural gas, the fire heat will be able to reach a higher temperature than in the base case. The use of electrical furnace to heat process streams was proposed as a means to reduce CO2 emissions. Other advantages of using electrical furnace include the use of induction heater can increase ethylene yield by generating a suitable temperature profile from precise heating. This is hard to achieve through conventional thermal stream heating, as in hydrogen base and base case. The heating element is also able to reach higher temperature compared to typical combustion products. This can lower the residence time of process streams at the lower temperatures. The absence of fuel also reduces the hazards from handling flammable or explosive fuels. This is the process flow diagram for electric-based naphtha cracking furnace. In the simulation, changes are made to the base case simulation, where heat X blocks are replaced with heater blocks using electricity as utility. For the R-plug block, a specified thermal fluid temperature profile is used to simulate the temperature profile of the wall of the reactor achieved through precise heating duty of induction coil. The temperature profile used is obtained from optimization for maximum ethylene yield from the reaction.
Hello, my name is Yushan again, and I'll be talking about the technical market and sustainability of our four processors. Now, for all four processors, our ethylene yield actually matches the range by literature, about 27 to 35 dry weight %. And this is actually proof that our simulation is sufficiently valid. Now, for all four runs, right, we have used Aspen to calculate our capex, opex, CO2 emissions, and ethylene production. The source of our feed renewability, the renewability of our source is also considered here. Now, capex is the estimated cost, does not include any land, rent, installation, or additional support structures. Now, we compare electricity and our base case, we can observe that the electricity is strictly worse than the base case, but a quite modest increase in our ethylene production, right? We incur significantly higher CO2 emissions and significantly higher OPEX. Therefore, we rule out electricity as one of our potential chosen methods. Now, comparing OPEX and CO2 emissions of the remaining three cases, we observe that an increase in OPEX actually results in a decrease in CO2. However, the increase for hydrogen gasification is actually quite high compared to the base case in hydrogen SMR, and we believe that it is too high to justify the decrease in the CO2 emissions, right? Comparing base case and SMR, we can see that base case, the SMR actually decreases the CO2 emissions by a significant amount, and we believe that it can justify the increase in OPEX. Note that both methods have the same exact ethylene yield, right? Therefore, we will choose, in this case, hydrogen SMR is the obvious contender. Now, the other thing is that due to sustainability and future-proofing our plant, right, we believe that hydrogen could be a fuel for the future. And if we already have a plant that accepts hydrogen fuel, then in the future, when we have a cheaper or maybe more commercialized source of hydrogen, we can use it, and we can combine it with our plant and can have a better, our plant can still function instead of the normal case where you use methane and you have to make changes, right? Therefore, we choose naphtha cracking using SMR generator hydrogen fuel as our chosen solution. Okay, thank you so much for listening.